So, hi everyone, welcome to the Thursday evening session. Hopefully you've been having a good conference. So our first speaker, we have two talks lined up for this session. Our first speaker will be Kevin Limanta from the University of New South Wales, who will be talking to us about a new algebraic interpretation of the super Catalan numbers.
Thanks, Fred. So I would like to start by thanking the organizers of this conference. I know they work very hard to make this conference successful, and so far it's been very successful. I see that, and I just want to thank them for working very tirelessly in this conference. So yes, I want to just maybe give like a very gentle introduction to my thesis. So I want to give some interpretation to the super Catalan numbers, the so-called super Catalan numbers, and it's going to be some algebraic flavor to that. Okay, so the motivation is that we want to set up some integration theory of polynomials over the unit circle. So this will be like, Fourier analysis flavored, but then over finite fields, basically. So the highlight of this theory is that it's going to be one foundation of Fourier analysis over finite field, but the functions that we're considering take value in the field itself or its finite extension. This is a different approach if you compare to the standard finite field Fourier analysis, when the function takes some element in the finite field, but then it returns some real number or complex number in the usual sense. Okay, but in this case, we're going to consider functions. We will be able to, with this sort of point of view, consider functions that take value in the finite field itself. And then we're not considering just the Euclidean geometry. Okay, so the circle that we're going to be investigating are sort of more general, and so over 3 geometries to be exact, and then all of them are connected, sort of in some sense. Okay, so what's the super Catalan numbers? So basically, these numbers are family of integers parameterized by m and n, and they take this form. So you have ratio of product of factorials, basically. And then, well, we can show that this is always an integer for any m and n natural numbers. And they have some combinatorial interpretations in terms of blossom trees, for example, proved by Schaeffer in 2003, cubic trees, big paths with some conditions. Okay, Kessel and Georgichuk and Orelowitz proved this separately. And then also Motzkin paths, so some sort of variants of big paths. And then you also have values of Graph-Choc polynomials. Okay, and the one that I mentioned last will play a prominent role in this talk. Okay, as values of Graph-Choc polynomials. Okay, so here are some values of these super Catalan numbers. See that if you look at the first row or the 0th row, and then, well, they are symmetric, so 0th row, 0th column doesn't matter. And you look at the diagonals, they are basically the central polynomial coefficients. Okay, and then if you look at the first row, okay, when m is equal to 1, and they are twice the Catalan numbers. So in that sense, they generalize the Catalan numbers. Okay. Okay, so basically a slight non-trivial identity. So basically in 2012, Georgiades, Munomasa, and Tanaka observed that we can express the super Catalan numbers as values of the Graph-Choc polynomials at some specific integers. So we define the Graph-Choc polynomial of order d and index j to be the one, this k sub j d And when x is equal to 2m and j is equal to m plus n and p is equal to 2m plus 2n, you have the super Catalan numbers up to some sign. Well, we have this identity. So basically, if you just consider the generating function of this Krausberg polynomial, you get this nice polynomial 1 minus alpha with the m 1 plus alpha to the t minus m, which then gives rise to this identity at the very bottom. So you can express the super Catalan numbers as the coefficient, the central coefficient of this polynomial, 1 plus alpha to the 2m, 1 minus alpha to the 2n, up to some sign. Okay, why the central term? Because this polynomial is of degree 2m plus 2n, and we're considering just the central, the one with power alpha m plus n. Okay, so the thing that I'm gonna be concentrating more in this talk is what I call circular super Catalan numbers. So basically, this is just the super Catalan numbers, but then you divide by some powers of 4. Okay, so it's gonna be rational numbers for start, and because we're dividing this by 4, okay, so if I take this modulo p for any odd prime p, it's always well defined. Okay, because Smn is always an integer, and then 4 is not equal to 0. Okay, we're not defining by 0 basically. And of course, in terms of this, the same sort of an analog, we have this scale polynomial. So 1 plus alpha on 2 to the 2m, 1 minus alpha on 2 to the 2n. Okay. Probably a nice thing about this. So this is the table of the circular super Catalan numbers. Okay, and then probably nice thing about this circular super Catalan numbers is it's like Pascal-like property. So that if you take any entry, so say this 1 on 16 in red, it turns out that that is always the sum of the entry right next to it and the entry right below it. Okay, so 1 on 16 is 3 on 128 plus 5 on 128. Okay, and that is true for any entry. So that's what I call the Pascal-like property. Right. So how do we connect this to the story of unit circles and stuff? So if you consider well, finite field of size q, which is some power of odd prime p, you can basically give that like sort of introduce a geometry. Okay, so through this symmetric bilinear form. Okay, so induced by this invertible symmetric matrix M. Okay, so in part of particular interest are 3 matrices I, J, and K, which then give rise to 3 unit circles, because once you have this symmetric bilinear form, you have quadratic form, and then you can just say, okay, unit circles are set of points x, y, such that the quadratic form, so that quadratic form is going to be 1. Okay, so I call them S sub G, S sub R, S sub B, of course with Q as well, because it depends on Q. And then this GRB basically stand for green, red, and blue. So I use colors to label them. Okay, so so this S sub B is your usual circle, okay, unit circle in Euclidean geometry, but then you also have 2 more circles, like sort of relativistic geometries. Right. So, well, because we're working in finite field, we have this possibility of, we have to be careful. Basically, there is a dichotomy whether -1 is a square or not, and then we utilize that. We distinguish that by the Legendre symbol. Okay, basically, in short, with this, you have this symbol -1 on P, which is going to be 1 or -1, depending on whether -1 is a square or not in that prime field. But over more general finite field, we have the Jacobi symbol to help us. Okay, right. So we have basically this lemma that is the size of the 3 unit circles that we saw before. So the green and the red circles. Remember, the green and the red ones are coming from the relativistic geometries, while the blue is coming from the Euclidean geometry. Okay, so the red and green ones, they're of the same size q minus 1, but then the blue one, we have to be careful. It's either q minus 1 or q plus 1. Right, so we want to define, because we want to basically come up with some sort of integral over a unit circle. So we want to come up with some notion of integral. Okay, and I call that circular integral functional. And basically, it is a circular integral functional when these three conditions are satisfied. Basically, condition 1 is that you want to map the polynomial 1 to 1 normalization. And then the second one, basically intuitively, if you have a function that restricts, sorry, if you have a polynomial that s functions restrict to 0 on the unit circle, then its integral ought to be 0. And then basically the third condition is saying that your integral should be invariant under rotation. Okay, and reflection, basically, in short. Okay, so that is motivated by the usual Riemann integral that we know. Okay, so that I won't go into details. Okay, like basically this introduction. But then, like, you can show that, well, these three functionals, okay, basically just like, you know, summing over the unit circles, which are finite in this case, you can show that these three functionals are indeed circular integral functionals, okay, in the sense that they satisfy the three conditions. But one of the big results that I don't talk here is that they are the unique circular integral functionals in its geometry. Okay, so that's one thing, okay, to show that they are circular integral functional, but to show that they are the only one, it's a bit more complicated. Okay, so now let's just assume that we have that as a given. So we know that these three are the unique circular integral functionals in its geometry, and our next task is just to come up with some formula, okay, to find this psi sub g sub r and sub b. Okay, well, we have an explicit formula for psi sub g. Remember, in the green circle, the defining equation is just xy equals 1. So it's simple, and it's either 1 or 0 for any given monomial alpha to the k, beta to the l. Okay, so the idea is basically just, well, if you have this green functional, you are basically summing over this this green circle, which can be thought of as summing over the multiplicative group of the finite field, and that's pretty well known because you can think of it as a cyclic group. Okay, so there is this divisibility condition appearing. All right, so what about the red and the blue one? So they are more complicated, but it's not very hard to show that, well, if you sort of define this special polynomial 1 plus alpha to the 1 plus alpha on 2 to the k, 1 minus alpha on 2 to the l, then a formula for the red functional is essentially that whenever you have this alpha to the k, beta to the l as an input, then the integral of that is either 0 if one of the power is odd, or this situation where you need to basically select some, you know, particular coefficients of that polynomial above, and then you reduce that modulo p. Okay, and that formula here depends on two things. That this formula depends on w and r. So, and then these two sort of depend on the size of the unit circle. Okay, so there is this sort of geometric constants that we need to be aware of. And the sketch of proof is, sorry, I'm just going too fast with that. Okay. Okay, where is, I'm not sure. Okay, so the sketch of proof is just, you know, from the green to the red ones, you consider this bijection basically. And that is well defined because 2 is not 0 in our field. Okay. Right, so what about the blue functional? Well, the blue functional is essentially the same for with the red one, except that you have this -1 to the n appearing in front of this f sub k comma l. So it's actually the same story, except that you have to be aware of some sign. Okay, so I want you to notice the similarity between the red geometry situation and the implicit appearance of this Jacobi symbol in the formula, because, well, remember the size of the blue circle is depends on whether -1 is a square or not in our finite field. Okay. So how does this relate to the circular super Catalan numbers? Well, when your powers of your input monomial is small, okay, like say k plus l is less than q minus 1 in this case, then basically this complicated looking formula reduces just to the central term of the this polynomial, which from how it's related to the Kraft polynomial, essentially just the circular super Catalan numbers. Okay, so we have this nice theorem. Okay, basically, if you wanna integrate alpha to the 2m, beta to the 2n, okay, then it's for small enough powers, then you basically have the circular super Catalan numbers reduced modulo p. Okay, well, we have some example. Okay, I don't really have much time left, but I'm just going to show you some example. Say you are in finite field of size 13, so it's a prime field. So -1 is a square in that field. So we have this, you know, -1 on q is 1, and then the size of the blue circle is 12, and in this case it's given by this one. So you can check that, you know, 2 square plus 6 square is 1 in F13. And of course, if I want to integrate alpha to the 4 beta square, then all I need to do is just compute this omega 2,1 and reduce that modulo 13, which in terms gives me 4. And then you can check that manually, and then you can also verify that it's going to give you also 4. Okay, so I'm not going to show you this example. It's pretty much the same, but just know that this works for, you know, more complicated finite fields. Basically, any powers of odd prime p. Okay, so how does it relate to the super Catalan numbers? Well, because we have this scaling, right? Basically, the super Catalan numbers, this is like 4 to the m plus n times the omega mn. We can think of the super Catalan numbers as the integral of this monomial over this circle of radius 2 in a sense, right? So we give them, like, you know, this is all algebraic because we don't employ any limiting processes, and they are in fact, you know, they have this analytic meaning as well in terms of in terms of Fourier analysis materials. Okay, so we have this sort of bijection from the unit circle to circles of radius 2 because 2 is not 0 in our field. Right, so I want to just spend the last minute of this just to like sort of muse around possibility of some further works. So remember that this super Catalan numbers is coefficient of the central term of this polynomial. Okay, what about, well, if one might ask, what about some formulas for, you know, terms that are close to central terms? So 1 step away, 2 steps away, and so on. Well, so one might define this S sub k. Okay, and what do we know about those numbers? So in fact, well, I like to tabulate numbers this way. Just stare at them like for some time and probably, you know, come up with some sort of rule after staring at them for like days. And I managed to find a formula for this S sub 1. Okay, so it's probably related to super Catalan numbers in a sense, except that you have this m minus n and then this m plus n plus 1 at the bottom. What about S sub 2? Well, this is a table of those numbers, and then, well, it's more complicated, but sort of similar in a sense that you have this m square, like this quadratic function, but then you also have m plus n plus 2 and m plus n plus 1. And then the rest is the super Catalan numbers. So it's actually very interesting, and I haven't found like a generic formula for S sub k yet, but I suspect it's not trivial. But I suspect, well, if you do further works, then this is the list of the polynomials that accompany the super Catalan numbers. So one might conjecture, well, so far that I see this generalized super Catalan numbers in a sense is taking this form, but then like well, it's an interesting question that I would like to prove someday. All right, I think my time's up. I'm gonna give it back to Fern.
Okay, thank you, Kevin, for a wonderful talk. That's all. Thank Kevin. So if you have questions in the chat, feel free to unmute and ask, or you can ask in the chat and I can read them out for you. Maybe I'll start. So you talked about this like result about the uniqueness of these functionals. Like, was that a surprise to you, or did you expect that there would be a unique one before kind of looking into it?
Well, the intuition should be that it is unique, but then like one need to develop a proper theory of how because we have to distinguish the notion of polynomials and functions when we are dealing with finite field, because two different polynomials might give rise to the same function basically in finite fields. Well, the surprise, I'm not surprised by the uniqueness, but then it's actually not an easy task, I might say, to develop the uniqueness. Yeah.
And I was also going to ask for at the end with the SKs. I mean, I know you only have sort of partial results, but are there any like generating function results? Can you find generating functions for these things?
No, so far not yet. So yeah, that's like one thing that I'd like to investigate further. But it's sort of like interesting to look at this table of numbers. I'd like to print out very big table of these numbers and just look at them forever, like finding some relation.
Yeah, how did you find that polynomial relation? That seems like finding you could kind of guess those factorials, but then how do you actually work out what polynomial it should be?
Yeah, I'm surprised myself. Well, one can see that the sort of Pascal-like property in this case can be generalized to this generalized super Catalan number. So you can sort of guess what. I have to like sort of guess the sort of form of this. So come up with this sort of form. Yeah, it's not easy, but once you sort of make a guess to one particular form, it turns out that it works. Well, yeah, it's very surprising. This one is very surprising. This one.
Any other questions for Kevin? Okay, in that case, let's thank Kevin again.
Thank you, everyone.